Okay, go ahead.
All right, let me move this up here. All right. Okay, so I read this paper, Vehicle State Estimation, based on extended Kalman filter in radio basis function neural networks by Y.Zha. I'm going to butcher all of their names, I'm sorry. C.Liu, F.Ma, and C.Liu. Let me, there we go. So I broke down the presentation in a few steps. I'm going to first explain the physical setup of the problem they're working with. So this is a self-driving, of course, kind of problem, but here on this figure, we can see what the setup of the problem is, right? So we have this. It is a little hard to understand at first. I thought it was two cars when I first saw this, but no, this is one car, and these are two wheels. This is the rear wheel, and this is the front wheel, right? So I think this is maybe like a common approximation for these problems. Instead of considering four wheels, you do two, and we just assume that it's the same for both rear and front, right? So
the bicycle model, right?
It's a bicycle model. Yes, exactly. I read that term before. It's a bicycle model. Yeah. Right, so on X, this is the direction that the car is facing. So it's the longitudinal vector they call. So we have a velocity vector for the car. It has a longitudinal component. We have for this omega r, that's the yaw rate, like how much it's rotating on this axis. And we have some extra variables here for the distance, like B and A, and the length of the car. But more importantly, we have the velocity calculated at each tire, right? So it's not the same as the car, because the car might be like rotating. So we have the velocity for the center of mass, and each tire is going to have a different velocity as well. Delta is the steering angle, right? So the angle between the tire orientation and the longitudinal vector of the car. And then we have these alphas, alpha 1 and 2. I'm sorry, the image is very low quality here. I didn't realize before. But these angles are between the tire orientation and the velocity of the car at that point, right? So it's not the same of this central vector here. It's this vector here. You want to calculate it at their center, right? So this is pretty much, oh, of course, another very important variable is beta. Beta is the angle between where the car is facing and its velocity. Right, so we have some forces here applied depending on this beta and all that kind of stuff. Right, we also have accelerations, AX and AY. So this is my first time looking at control theory stuff. So a lot of this stuff might be familiar to a lot of people, but it wasn't for me. So they often break apart the problem into state variables and observation variables and input variables. So the state variables is basically just whatever defines the system completely. So in the case of pendulum, that would be the angle and the angular velocity, for example. And here we have we can consider like the omega rate, the beta, and the velocity of x. This is not necessarily doesn't have to be necessarily organized this way, but this is just an example. The observation variables are the things that we actually observe, like our sensors, the things that we can actually see. So for example, lateral acceleration, that's something that we can probably measure. And input variables are things that we can control directly. So they show up in the dynamics equations as forcing terms, things that change other variables. And so the problem is that you say you have inputs and observations. We want to estimate the state of the system completely for the next moment. So for the 2 degrees of freedom time model that they use, we consider the state to be completely defined by the omega rate, which is the yaw. Sorry, they call it the yaw rate, which is the angle that the car makes with the direction it's going, and beta, which is the angle between the car and the angle of its its vector velocity. Sorry. So these are the equations that define this system, the equations of motion, right? And we can see here that we also have velocity x, the longitudinal velocity. For the 2 degrees of freedom model, we treat this as a known variable. We known as known as we know what it is, whether it's constant or whether it's just a perfect measurement of its value. So, so again, in control theory, we can put that into the state observation input terminology, and we get like this equation here. It looks like a vector equation, right? Matrix. And the reason we do this is going to be clear when we do like Kalman filters, because we expect things to look like this. Right, so just to name things, we have x dot. This is not the x and y from the coordinate system that we saw in the figure earlier. This is just x representing state and y represent observation. Right, so x dot, we can see here that it's the derivative of yaw rate and beta. And then A and B and C, A and B are defined by these other parameters of the system, the velocity. Y is the observation. These are the things we measure in this 2 degrees of freedom model, which is the omega rate and the beta. Realistically speaking, this is not realistic at all. That's what, but they do this because for the 2 degrees of freedom version of them, it's simpler, it's easier to calculate, even though it's not very realistic. Like we can't have, like, it's very difficult to have good sensors for these specific quantities. And U is the input, which in this case is just the steering angle. Now, for the 3 degrees of freedom version of the model, things get a little more complicated. We now consider the longitudinal velocity to be a variable of the system. So now it gets included in the dynamics, right? So it's going to be driven by its velocity, beta, and the acceleration. Now, this is much more realistic because the observation part of the system now is just the lateral acceleration, AY. Not this one, sorry, AY. This we can put sensors to measure. Like acceleration is easier to measure than perfect positions and velocities. Right, so putting it in the same like matricial form for later, basically the equations of the system are going to look like this, right? So it's basically the same equations before, just written in a different form. And K1 and K2 are just encoding some other parameters. And this is the observation function, just for the AY. So this time, observation is just one variable, it's just AY, and it's given by this. It's important to notice that this is not a linear equation, nor it's this one, right? Because we can see that K1 appears there, and we have Vx there. We also have K2. We have Vx here and here, right? So it's not linear.
But why is acceleration easier to measure?
Oh, that's just my intuition, I think. I guess if you have like a camera outside of the car to get perfect positions, you could do that. But acceleration sensors are just like a spring that you measure how much the spring is moving and stuff like that.
I see.
I'm just using my intuition. I really don't know. I could be wrong. So anyway, so we want to learn how to predict the state of the system. So one of the methods is called a Kalman filter, which supposedly it's good when you have Gaussian noise in the measurement, specifically Gaussian noise. If it's not, it's not good. And basically works like this. So you have a state and have some equations that predict it, and you have some measurements. So the idea is first you do the physics forecast. So we do the basic prediction as naively as possible, just make a guess. And then we measure what we got, and we account the noise for the next step. So the next step, we're going to make a prediction, but we are also going to include the noise that we got for last time. So it tries to self-correct. That's basically the idea of a Kalman filter. but it's yeah, I'm just going over a little more of the thing. So we predict where the state of the car, where it is, then we measure what I call the residual, which is so this is what the actual sensors measure. And this is what the sensor should be measuring if the prediction is right. And we use this R here on the next prediction. And so it goes in there. And this K is just like a weight of how much we want to impose the correction. So okay. So it needs the equations, dynamic equations to be linear. That's the most important part, which I think are true for the 2 degrees of freedom model, but not for the 3 degrees of freedom, where we made the longitudinal velocity part of the system. So the extended part of the Kalman filter algorithm is to basically make an approximation, make a Taylor series of the functions and just disregard everything after the first order. So in practice, that means we have to calculate the Jacobian matrix of both the state and the observation function, which is these two, right? So we do this and we throw away everything else. So this is the Jacobian for both the state and this for the observation. And this is already linearized. So it's we already threw away a bunch of all of the other terms and just stuck with the first terms. We can switch to the PDF if just to take a quick look at the steps that they got to get there, because I think it's interesting to look at this thing. Right? So here we have the state equation. This is in its perfect form. No linearization occurred yet, so it's just a state function. But we add a noise term. So this Q is a noise term. And we do the same thing with the observation. We add another noise term there. We make some assumptions about this Q. It has to be like it's constant and diagonal, considering square value of the expected maximum variation of the state variable. Anyway, it's just a noise and it has to be kind of Gaussian, it has to be well behaved. Right, so we're going to calculate the derivatives, and that's how we got to that equation that I put on the thing. Right, so here's just the steps that I described earlier. So let's go back here. So that anyway, this concludes the EKF part description of the algorithm, how you predict the system by linearizing the equations of motion. So the other method is called RBF, which is a radial basis function. And so the idea is, I initially thought, okay, so you're going to train a neural network to predict the thing as a black box, but it's not that complex actually. This is a very simple neural network. I don't know if this is like common knowledge for people from machine learning, but to me it was quite new, and I had to do a little bit of research to understand what it is. So it's a very simple neural network. It has an input layer, and then we have one hidden layer, and then linear output. So this particular, it's just one hidden layer. So it's very linear in nature, but it has an activation function that it's very special. Like instead of just a bunch of weights, it's actually a bunch of Gaussians on input space. Let me stop talking, just show the thing. So it needs a lot of training data. That's the weakness. But let me go here. So this figure here they put on the paper, to me, it tells me very little. I can more or less understand what's going on, but very little about it. I mean, I can see that it's the input layer, the hidden layer is here, and this should be the output. But to me, this is confusing. So I was trying to explain to myself exactly how this works in practice. So we put a lot of training examples during the training. And so the training is going to define the neural network to have a bunch of different nodes in this hidden layer. Each of these nodes is going to be like a Gaussian, like center that I'm calling them like memory blobs. I wrote here memory center because it sounds better, but it's basically saying, hey, this if you have an input that's more or less like this, you have like 15 degrees steering and you're braking and whatever, then this is the output should be. And then you fill the input space with these different blobs and you interpolate them. That's what the network is doing. It's just you give it a new input and it looks for the nearest memory blobs and just interpolates between them, and that's what it outputs. That's what I got from this anyway. So that you give it a new input, here we go. To have a steering of 12 degrees and have an acceleration. And how similar is this to what I remember? So it gives you this thing here. So you do this for the nearby memory blobs, and you do like a little average. So the training is all about finding the positions of these memory blobs, their sizes, which is the sigma, and the importance that we attribute to them with this weight. Which
So
is
the
what I just said.
activation function is the Gaussian. That you're saying?
Yes, exactly.
Okay.
It's a single hidden layer, but the activation function is a Gaussian.
So it's not linear, you know.
It's not linear, no.
Okay.
The activation doesn't make it linear. No. It's linear just in the sense that you have only one input mediated on there.
Simple, but not linear. Okay.
Simple, exactly. So basically what this is, it interpolates between data points, not necessarily directly training, but basically training data. Well, let me just say this a little. Okay, so so that closed the RBF part. Okay. So what the paper is actually doing, they're combining both of these algorithms on the fly, EKF and RBF. And the reason they do, the way they're doing this is first they get reference values, and the reference value uses the 2 degrees of freedom model using Kalman filter integration, right? So they use the simpler model, the one where we assume perfect knowledge of the longitudinal velocity to serve as reference. And then they compute the errors of the EKF with the 3 degrees of freedom model against this reference, which is obtained before. And then we do the same for the RBF against this reference again. So we attribute weights to these errors, and the final estimate is going to be that, right? That's what it's doing. So supposedly what this is doing is that when EKF struggles, then the RBF is going to get better. When the RBF struggles, the EKF gets better results, at least according to the reference values. Right, so this assumes that they have not competing attributes, but like one is bad, but the other is good. That's the idea here. So they calculate the performance of the system. Like, so this error here that we're seeing, this is for your rate and longitudinal speed. This is not against the reference. This is against perfect knowledge. Like they're calculating the absolute error against ground truth. So just EKF has this error, 0.5, just RBF has 0.4, and the fusion has 0.2, so it performs a lot better. And this is same thing for the longitudinal speed, right? So terrible, okay, good. Yeah, and that's interesting that it works. My personal questions that I had with this is first, real-time feasibility. We're doing copying the reference using Kalman filters on the 2 degrees of freedom. We're doing the EKF on the 3 degrees of freedom. We're doing the same with RBF, and then we're fusing them. I don't know if this is something you can do in real time. I don't know why they use the simplest one as a judge. I don't understand exactly that. I mean, that should be the least reliable of them, but I mean, the data looks great, so I guess that makes sense. But I would like to see the reference shown in this table here as well, because I have a feeling that's going to be very similar to this fusion error, because that's what it's doing, right? We're choosing between the one that's closest to the reference. Why not just use the reference directly then? I don't understand that. Yeah, so those are my questions. What are your questions?
All right. Very good. Thanks, Diego. Any questions, comments?
We have some more plots here from the paper if you want to see.
So have they made any comparison like with other states of the art or
No, not. I didn't see anything like that.
just that the fusion works better than individuals?
Yeah.
That's the only, right? Okay.
Yeah, and why not use just the reference directly? I mean, it seems like it's faster to calculate and it seems better than both.
I don't think like calculation speed would be an issue for
Yeah, maybe not.
yeah, so that should be instantaneous. All right. Questions? Okay. Thank you, Diego. That was good. Thanks.